Myself, Minu Joske, Assistant Professor, Mathematics Department, Jyoti Engineering College, Chirudurti. This is the second class on Fourier transform. We will discuss some problems for this Fourier transform. Find the Fourier sine transform of f of x is equal to e raised to minus x, and hence show that pi by 2 e raised to minus m is equal to integral 0 to infinity x sine mx divided by 1 plus x square dx. That means we need to prove that the value of this integral is equal to pi by 2 e raised to minus m, and for that we are applying Fourier sine transform. So since we need to prove the result by using Fourier sine transform, we will write the formula for Fourier sine transform. The formula is root of 2 by pi integral 0 to infinity f of x sine lambda x dx. Now the function f of x can be taken as e raised to minus x. Since here it is given f of x is equal to e raised to minus x, we will take this f of x as e raised to minus x. So that root of 2 by pi integral 0 to infinity e raised to minus x sine lambda x dx. Now in class 1 already we have discussed the formula for integral over 0 to infinity e raised to minus x sine lambda x dx, and it is given to be lambda by 1 plus lambda square. So that the Fourier sine transform of e raised to minus x becomes root of 2 by pi lambda by 1 plus lambda square. Since we need to prove this integral value, we will take the inverse of Fourier sine transform. So the inverse Fourier sine transform is given by the formula f of x is equal to root of 2 by pi integral 0 to infinity fs bar of lambda sine lambda x d lambda. When we will substitute for this fs bar of lambda, and we will try to get this result, and for that 2 by pi into root of 2 by pi into root of 2 by pi totally becomes 2 by pi integral 0 to infinity lambda by 1 plus lambda square, which is the value of the Fourier sine transform of e raised to minus x into sine lambda x d lambda. Now we could replace this f of x by the value e raised to minus x that is given in the question, so that this becomes e raised to minus x into 2 by pi integral over 0 to infinity lambda sine lambda x by 1 plus lambda square d lambda. Now replacing this x by m to achieve the desired result, so that it becomes e raised to minus m 2 by pi integral 0 to infinity lambda sine lambda m divided by 1 plus lambda square d lambda. We are replacing this x by m in this equation, and we are reaching this result, which is same as integral over 0 to infinity x sine mx. That means we are replacing this lambda by x sine mx by 1 plus x square dx is equal to pi by 2 e raised to minus m. So to prove the result, after finding the or after taking the inverse Fourier transform, we are replacing lambda by x and x by m, so that we are reaching the required result. Next question. Find the Fourier cosine transform of f of x is equal to e raised to minus x, and hence show that integral 0 to infinity cos mx by 1 plus x square dx is equal to pi by 2 e raised to minus m. So using this Fourier cosine transform of this e raised to minus x, we need to prove this integral value. So for that, we will take the Fourier cosine transform of this function f of x. So by heart the formula, we know the formula for the Fourier cosine transform. Fc of f of x is equal to root of 2 by pi integral 0 to infinity f of x into cos lambda x dx. Now we could replace this f of x by e raised to minus x, which is given. So e raised to minus x into cos lambda x into dx. In class 1, we have discussed this integral value, and that is equal to root of 2 by pi 1 by 1 plus lambda square, and I call this as equation number 4. Now we will take the inverse Fourier cosine transform of this equation 4 to reach the required result. So that inverse Fourier cosine transform formula is f of x is equal to root of 2 by pi integral 0 to infinity fc bar of lambda cos lambda x d lambda. Now replace for the Fourier cosine transform fc bar of lambda can be replaced by root of 2 by pi 1 by 1 plus lambda square. So that root of 2 by pi into root of 2 by pi becomes 2 by pi, and this fc bar of lambda is equal to 1 by 1 plus lambda square cos lambda x d lambda. The required result is cos mx by 1 plus x square dx is equal to pi by 2 e raised to minus m. So to bring this pi by 2 e raised to minus m, I will write this f of x as e raised to minus x, so that e raised to minus x is equal to 2 by pi integral 0 to infinity 1 by 1 plus lambda square cos lambda x d lambda. Now take this pi by 2, 2 by pi to the left hand side. It becomes pi by 2, and before that we are replacing every x by m as we have done in the previous problem. It is a raised to minus m 2 by pi integral 0 to infinity cos lambda m divided by 1 plus lambda square d lambda. And since the question is given in terms of x instead of lambda, finally we will replace this lambda by x and we write this 2 by pi in the left hand side. So it is pi by 2 e raised to minus m is equal to integral 0 to infinity cos mx 1 plus x square dx. So this is the result regarding the Fourier cosine transform of e raised to minus x, and the previous one was the result regarding the Fourier sine transform of the same function e raised to minus x. Now we are discussing the Fourier transform of the function e raised to minus x square by 2, and we will prove that Fourier transform of this e raised to minus x square is self-reciprocal. So by the term self-reciprocal, we mean that after finding the Fourier transform of this e raised to minus x square by 2, the result will be in terms of this e raised to minus x square by 2 in some other variable, so that we could call this as e raised to minus x square by 2 as self-reciprocal. The Fourier transform is given in terms of the same pattern. That's why we are calling it as self-reciprocal. So we will check how we can prove this result. So the Fourier transform of f of x is given by the formula f bar of lambda is equal to 1 by root of 2 pi integral minus infinity to plus infinity e raised to I lambda x f of x dx. And we will take this f of x as e raised to minus x square by 2. So e raised to minus x square by 2 e raised to I lambda x dx. Actually, we need to integrate the function, but the direct integration is not possible. So we will make this as a perfect square. So to make it as a perfect square, we will add and subtract the suitable term. So for that, first of all, I will take this LCM. So we could write this minus 1 by 2 outside. So it is x square. This will be negative minus 2I lambda x dx. Now, to make it as a perfect square, I will add and subtract I lambda square. So this is I lambda square minus I lambda square. And we could combine these these three terms to make in the form x minus I lambda the whole square. So this becomes x minus I lambda the whole square, and this I square becomes minus 1, and this lambda square exists. So this term can be written like this, plus I square lambda square divided by 2. So this is e raised to minus 1 by 2 into x minus I lambda the whole square, and this could be written as this I square is actually minus 1. This minus into this minus can be taken here. It is e raised to minus lambda square by 2 integral e raised to minus 1 by 2 x minus I lambda by I lambda the whole square. Now also the integration is not very easy. So let I take this term as z. X minus I lambda be equal to z. So we could find dz becomes, from here we could find dz becomes dx, since we are having lambda as a constant term. So instead of this dx, I could rewrite it as simply dz, and this term becomes minus z square by 2. Now, this is 2 e raised to minus lambda square by 2 by root pi integral 0 to infinity e raised to minus z square by 2 dz. Now we know we are writing this form, we are writing this 2 here because we could see this is an even function of the variable term z, and it varies from minus infinity up to plus infinity. So write it as 2 into e raised to minus lambda square by 2 root 2 pi integral 0 to e raised to 0 to infinity e raised to minus z square by 2 dz, identifying this as an even function. So that this is equal to e raised to minus z by root 2 the whole square. Now to integrate the term, I will take this z by root 2 is equal to some t. So dz becomes root 2 dt. Now the limits are same, it does not change. So it is integral 0 to infinity e raised to minus t square dt, and this integral value you need to by heart, it is equal to root pi by 2. Replace the value here. After cancellation we will have the result as e raised to minus lambda square by 2. That means the Fourier transform of e raised to minus x square by 2 is equal to e raised to minus lambda square by 2. That's why the name this function e raised to minus x square by 2 is self-reciprocal with respect to Fourier transform. We will discuss more problems in the coming classes. So thank you for now.